Hi, welcome to chapter 15. You may be asking yourself what happened to chapter 14. In the interest of time, we're going to be moving on from the geology portion of this class to the oceanography chapter. So we had to cut something, and glaciers and deserts was the thing that was cut. So moving on to chapter 15, we're going to be covering our oceanography chapters. And chapters 15 and 16 are our two oceanography chapters. So when we start looking at oceanography, we really need to start talking about water. And the Earth is considered the blue planet, not because of the blue skies that we have, but because the vast majority of the Earth, 71% of the Earth, is covered by water. Now, when we start looking at the Earth itself, we need to talk about where we are on Earth. And prior to GPS, we had a little bit of a challenge trying to figure out where we were on Earth, especially if you're in the middle of an ocean. You're not going to be able to use a landmark like, say, the Mineral Area College. You know, I'm south of Mineral Area College or north. If there's nothing but water around you, you're going to be really, really, really potentially not very accurate unless we used something like longitude and latitude. Now, latitude was the easy portion. Latitude was measuring how far north or south of the equator we are. And we know that on March and September 21st, the sun is directly at the equator, as it's showing in this image here. And so then if we looked at noon on the equator, we know where the sun is shining directly at that spot. You would not have a shadow other than right underneath your feet. Now, here at Mineral Area College, we're a little bit further north, and so we do have a shadow, and so we can, over the course of the year, the sun will shine directly at 23.5 degrees north and 23.5 degrees south. You could actually calculate the latitude at any given date if you know what the date is. You could figure out where the sun is shining most directly, and we know that the Earth is a curved surface. So with a little bit of algebra, we could actually, or a little geometry, we could figure out exactly, based on your shadow, you could find exactly what your latitude is. Now, that's latitude. Remember, north or south of the equator. And that one's the easy one. Longitude was a little bit more difficult because we don't really have the sun as a frame of reference. We have arbitrarily picked Greenwich, Greenwich, England, as 0 degrees longitude, and we're measuring from a circle how far away east or to the west of Greenwich mean the prime meridian, or the original meridian. And this was very, very difficult to do. In fact, we weren't able to accurately do this until significantly later. In fact, one thing that really made this possible is the use of a clock like this one. And this clock is very unique for its time. In fact, it was basically a competition was held to form a clock like this, because prior to this, if you wanted to measure time, you used a pendulum clock. And this was great for moving back and forth. We could keep very accurate time with this. But in an ocean with the water moving back and forth in the boat, this would not be a really great, this wouldn't be a great tool. And so what we as humans did, we actually initiated a prize. We're in the middle of the pandemic right now, and there was a lot of money that was sent out to try to develop a vaccine. Hopefully everything, excuse me for a second. Sorry about that. So we're in the middle of the coronavirus pandemic, and so there's a bunch of companies that are given some money to hopefully develop this vaccine. There's been a lot of these prize offerings to make these scientific advancements, to develop a commercially viable way to get into space was another of these giant X prizes. And so this was one of these other giant prizes. It was to develop a clock that would not need a pendulum. And so there was a carpenter named John Harrison who took it upon himself to make one of these um, clocks, and you can see he made, I believe, 3 of these clocks, and then they had to test this clock, and these clocks could not be off by just a fraction of a second, because then you'd have to reset your clock. And if you're out at sea for multiple days or months, a little bit of time off every single day would accumulate, and so this would be a bit of a problem. So here's a map or a globe, and I mentioned latitude. Here is what's called an analemma, and this is used to determine where the sun would be at any given time. So you could look at your latitude and determine where the sun should be and what kind of a shadow you are having, and use that to find your latitude. But the longitude does require a clock, because if you know that we are traveling around the Earth once every 24 hours, so 360 degrees every 24 hours. That means that 1 hour would represent 15 degrees of longitude. And so you'll notice on this map here, with the advent of the longitude, we could then calculate, if we looked at from noon to noon, we could actually calculate the Earth's rotation, or you could see how fast you're going and what your latitude is using this using a clock. And so this map was actually we explored before we actually knew the longitude, and this became very difficult to try to figure out how big these oceans were. This is a map from your textbook showing the Dutch cartographer showing the coastlines that we knew at this time. So mapping along the coast was not as difficult as trying to figure out how big the ocean was. Is it much more narrow, or is it much larger? And so you can see that these a lot of times this might explain why not knowing how big how much water had been traveled, why there's a misconception that people thought that the Earth was flat when at the time that Christopher Columbus was sailing across the ocean as he knew it, he thought he traveled a lot further, and really what he did was he traveled a much shorter distance and found the western continents of North and South America when he thought he had crossed into India. When we start looking at oceanography, once we had the ability to really accurately measure longitude, now we can really start studying the ocean floor, and we can study with the shape of these continents. And so we have a lot of different methods for monitoring the ocean. Obviously boats, sailboats, which would follow these very precise patterns as a result of wind and ocean currents. We'll talk about these trade winds, and this was great for using sails. However, this was a bit of a problem if you were going in the exact same way. You would be subject to pirates, and so knowing these trade routes was a kind of a double-edged sword. We've got some other modern boats over here. The Woods Hole Institution of Oceanography has a research vessel here. This one down here looks like a deep sea robotically operated vehicle, or ROV. This looks like a side scan towfish. Basically a device that would be carried behind a boat and using sonar. It looks like another manned operated vessel down here. And then the last image that we have here is a satellite. And you may say, what are we doing with a satellite to measure oceanography if we're out in space? Well, first of all, the coastlines are pretty easy to measure. The other thing that we can use to measure when we start looking at the ocean, even though Visible light doesn't pass through the depths of the ocean. Radio waves don't travel through the depths of the ocean. But we can, in fact, measure where there's some large features like a mountain range or a valley, both of which are going to be represented on the sea floor. If we have a mountain, say the mid-ocean ridge, what's going to happen is water is going to pile up around those areas because it's going to have a greater gravitational pull, and so the water is actually going to mound around that location. And the same thing holds true with a cavity like a trench. Prior to this, it becomes very, very difficult to measure the seafloor. We would literally have to go and drop a line and go the 2 miles or so of water until we hit a piece of sediment, and there's usually a piece of tar at the bottom attached to that steel slug. Then they would bring this up and say, "Up, we hit water, or we hit soil sediment," and so I know the seafloor is my line was longer than the seafloor. And so through trial and error, you could actually figure out about how deep the water was at that one spot. And so here's a map of the predicted seafloor based on those satellite images. And here's a higher resolution of the seafloor. But when we start looking at the seafloor, we divide the ocean into different basins, as well as into individual ocean basins, as well as seas or bays. And so here are some common bodies of water that are all looking at saltwater bodies here. And so when we start looking at the ocean floor, we have not mapped at high resolution most of the ocean floor. We've mapped about 5% at high resolution. And the vast majority of the ocean has been mapped at about a 5 kilometer or 5,000 meter resolution. We can contrast that with Mars. Mars has been mapped at a 20 meter resolution, and I believe the moon has been mapped at about a 7 meter resolution. Every single, and what I mean by that is we can look at a computer screen, we can look at pixels. Each one of those pixels would represent a square, and what we're looking at for a 20 meter resolution is 20 by 20 square. What is the elevation at that point? And then when we start looking at these 5,000 kilometer or 5,000 meter resolutions, that's 5,000, about 1,500 feet, so about 3 miles. So when we start looking at this, run a 5K. That's take one reading along that spot in that 5K, and that's the location, or that's the elevation of that entire surface. You can see where a lot of errors might have be developed. So when we start looking at sea level is defined as the elevation of the boundary between water and land, where the water is below and the air is above. And that changes quite a bit. And so in a math class, you may have looked at mean means average. And so we start looking at mean sea level. This is the average sea level of a boundary of between the ocean and water over the course of a given year. And so sea level is constantly changing. And so we start looking at sea level. There's a number of different reasons why sea level can change. This point there is the red line on your graph is showing where current sea level is. And so some of these sea level changes are a result of a couple of different things. One of which is when we start having a lot of divergence, a lot of materials coming up out of the interior, right at the mid-ocean ridge. And that rock's got to go somewhere. So if it fills in the ocean basin, well, if you have a lot of eruption taking place, the water's going to have to go up a little bit further later. If we have a bunch of ice and we throw ice onto land, well, the water's got to come from somewhere, and so it's not going back into the ocean, so that's going to cause sea level to drop. And so there's a number of different factors when we start looking at sea level change. If we look at the same quantity of water, If it's warmer water, it's going to take up more space. It's less dense. Water is most dense right about freezing, just a little bit above freezing is when water is most dense. And so if we start heating up the water is going to take up more space. And so when we start looking at sea level, it is constantly changing. It is a very difficult measurement to take, is what is sea level at. And so when you look at a topographic map, not only will it tell you what zero is or sea level is, what year sea level is was measured, and so they use the same measurement year after, at these different. 1927 is a fairly famous measurement year for sea level. So when we start looking at water in the oceans, one of the big components of distinctions of water in the ocean compared to water, say in our drinking water, is the salinity. Water is about 3.5%. Ocean water is about 3.5% dissolved minerals. The vast majority of those minerals are sodium and chloride. You know it as salt. NaCl. Na for its original, the Latin name natrium. And so NaCl. And so we can see that if we looked at an average kilogram of water, or 2 pounds of water, about 965 of that water would be would be fresh water if we started looking at a kilogram of salt water. The remaining 35 grams, or 3.5%, is in fact salt. Again, most of it is sodium chloride. But then we have just about all the other elements on the earth are found in the water in small quantities. Now, if we start looking at small quantities, they can add up to be huge amounts. If we start looking at, say, gold, we're talking 13 parts per trillion, per billion. But if we start adding up the vast majority of water, that's more gold than we have ever mined in the history of Earth. So little bits of water, there's just a lot of water is my point in that. So we start looking at what is the vast majority of salts in the ocean. Sodium chloride, which we know as the mineral halite. So when we start looking at salt in the water, salt is going to make the water more dense, more thick. And so if we had really salty water, you could actually float fresh water on salt water. And there actually can be a density difference. Now, what's going to cause water to become very salty? In these subtropical areas, these are where we have giant deserts of the earth. And these deserts have lots of evaporation taking place and little rainfall. And so in areas that you're drying out, having little rainfall and lots of evaporation, you're going to have lots of salty waters. Now, the salt originally is a product of weathering and outgassing from the volcanoes. And so this is the original source of this material, but you can really concentrate it at areas that you're having lots of evaporation take place. If you have glacial melt, you can end up with lots of water washing off the continents, lots of fresh water washing off. Then you can have quite a bit of fresh water, and so lower salinities. And so this is why we have these areas of exceedingly high salinities, is because those are areas that we have very little rainfall. And so the boundary between surface water salinities and deep water salinities is known as the halocline when we start looking at salt, the salt boundary. Cline just means bend, and so when we start looking at the halides, so this is a boundary between the freshwater between the surface waters and the water at depth. When we start looking at water at depth, it all becomes very much more uniform, but around the equator, we have lots of rainfall occurring. And if we have lots of rainfall occurring, we end up with lower density of water. Lower density of water. If at high latitudes, we have little evaporation taking place and we've got a lot of water washing off the continents. And so that's going to create a really low, not much of a halocline. But in those tropical regions, those 30 degrees north and south latitudes, those giant deserts of the world, those areas are going to be really, really high salinity at the Earth's surface. But then at depth, the water becomes less salty and creating those haloclines. Now, when we start looking at temperature, we can start looking at high latitudes, the tropics and the equators. At these high latitudes, again, when we start looking at latitudes, 90 degrees is the highest latitude you can have. So high latitudes are near 90-degree latitudes. The water is going to be really cold. It should come as no surprise that near the North Pole and the South Pole, you have a lot of cold water. And so cold water, I mentioned, is very, very dense. And so there's no real movement of this water. When we start looking at the equator, there is a water near the Earth's surface is really, really warm, 25 degrees Celsius, not 25 degrees Fahrenheit, but 25 degrees Celsius. That water is really, really warm. But then once we lose the penetrating power of the sun, the water at depth can't be cooled. And so you're going to end up with a thermocline. And so a thermocline is a bend in the temperature graph. And so around the equator, we have a really distinct thermocline. And in the tropics, we have a little bit of one of these thermoclines. Now here in the upper to mid latitudes, we have thermoclines that only occur during our summer months. And then during the winter months, we don't have a thermocline. We end up with water that's cold all throughout. And we break these thermoclines twice a year and cause a lot of mixing of water to take place. So when we start looking at water densities, again, it's a function of both temperature and salts. And so when we start looking at these, you're going to end up with a lot of a sinocline, a density difference between the water near the surface, which are going to be less dense, and the water at depth is going to be a very much higher amount of density. And so this water is just going to have a tendency to be layered. You may have seen oil sitting on water, and this is the same density. We'd have a sinocline right at that interface where that oil is sitting on top of the more dense water. If you were to try to mix this up, it would eventually separate back out as this density difference between those two materials. And so when we start looking at where we have these lower density above and higher density below, this would be one of those sinoclines. Now, when we start looking at oceans, they're always moving as a response to a couple of things, one of which is wind. The other one is due to density. And so when we start looking at an ocean current is defined as a band of a flowing water that moves faster than the adjacent water. And so when we start looking at this Gulf Stream, it was first described by Benjamin Franklin, who identified that some boats were moving merchant ships were moving faster than the U.S. Postal Service. And as a result, he investigated why this was taking place. And we learned that this Gulf Stream was very, very, very important for moving waters across the Atlantic Ocean. Now, at depth, we have water. We do have deep water, deep sea currents, which also are occurring. So when we start looking at surface currents, the upper 100 to 400 meters of the ocean of water are caused by, going to be caused from wind and the frictional drag of wind. So the winds are moving in one direction, it's going to bring with it a little bit of water. So when we start looking at some of the winds and wind surface currents, the winds by and large from about 30 degrees to the equator are moving from the northeast or the southeast, depending on which hemisphere. We have giant winds around here moving from the west to the east. These are called the westerlies. And near the poles, they're moving from the east. And as a result, these ocean currents are going to be moving in these long bands, creating these ocean loops or gyres. And these gyres would be much larger if we didn't have these continents getting in the way. But when a ocean gyre hits a continent, the wind is deflected. We can see this much larger gyre in the largest ocean in the Pacific Ocean. And when it hits a continent, it gets deflected. Now, when we start looking at these patterns, in the northern hemisphere, these deflections are to the right, creating these clockwise loops. And in the southern hemisphere, they're creating these counterclockwise loops. And if the ocean currents are coming from the equator, going towards the poles, they're going to bring warm water. And we start looking at the water from the poles towards the equator, it's going to be cold water. So if you were asking to go into the water at the same latitude, we can see that California would have colder water than Florida, bringing up that same latitude, same amount of sunlight difference in the ocean water temperatures. So these gyres also will create some areas that don't have much movement, and they just are circulating a lot, swirling around in the middle of these gyres. And so if you had something that was floating in the water, it would get caught in these eddies. And one of the most famous examples of these is the Great Garbage Patch here, imaged on the right. And we can see where they're located. They're in the middle of these gyres. And so when we start looking at these global winds, about 2% of the energy is transferred from the winds to these ocean currents. And so this is what is causing these ocean winds. And so we can see we have the trade winds located near the equator. We've got the westerlies over here from the west. And then not shown on this map here, because it's near the North Pole and the South Pole, are the easterlies. And so, or the polar vortex you may have heard about in the last couple of years. We can talk about the impact on meteorology. We can look at that polar vortex which is an easterly moving winds. Winds are always named after where they come from. And so, again, the winds are moving over the water, and so these ocean currents in blue are a direct impact from the surface winds. So when we start looking at the Earth, one thing you'll notice is that the Earth is constantly spinning, and as it's moving every one day, it does one lap, one circle to create a 24-hour cycle. And so that means that if you're at the North Pole, you're not moving very fast compared to if you're at the equator, when you have to go one lap around the Earth. And so the water is moving at different speeds. And well, the Earth as a whole is moving at different speeds. Now, in addition to this, we are moving around the sun, and we're 90-ish million miles away from the sun. And so as we're doing one lap around the sun and over the course of 1 year, the North Pole is still moving. But when we look at the different points on the Earth, the fact that the Earth is spinning, this is the speed that we're looking at on this chart here, showing that at the North Pole, you're moving virtually one rotation every 24 hours. But as you get closer to the equator, you're moving a lot faster. It's this movement, the centripetal forces actually cause the Earth to not be a perfect circle, but to be a little bit wider around the equator than it is at the North Pole. As a result, the gravitational pull, which is a function of how the force of the mass of yourself and the mass of the Earth, but the distance is going to be a little bit further, and so you're actually going to weigh less if you were actually to step on a scale on the equator versus the North Pole. So when we start looking at the Earth, we can see that if we had an air moving from the North Pole to the equator, the red arrow is showing what the actual path would be going from the North Pole to the South Pole. And you can see that in this image, it looks like, from viewed at the North Pole, it looks like the Earth is moving in a clockwise fashion. If we look at a counterclockwise fashion, if we start looking at the South Pole, it looks like it's moving at a clockwise fashion. It's this difference between the perspective from the North Pole and the South Pole, which causes winds to move in opposite directions. You may hear about things moving differently in the Southern Hemisphere. And so I'm going to try to focus all of our discussion towards the Northern Hemisphere, where this deflected path of wind movement is going to be to the right. And so if we start looking at this image here, the red line here, it would be deflecting the winds to the right. Now, if we start looking at the blue line, it's also going to be to the right. If we're moving from the equator, we're going a lot faster than if we're going from the equator to the North Pole, we're going a lot faster at the equator. And so this excess amount of speed is going to result in this apparent deflection. And so both of which are going to be caused from the fact that the Earth is spinning and the Earth is a sphere. And so collectively, we call this the Coriolis effect. Again, in the Southern Hemisphere, it's going to be the exact opposite. Things are going to be deflected to the left. And so in the Northern Hemisphere, it's to the right. And so this is caused from the fact that the Earth is spinning, the Earth's rotation. Now, at depth, some of that energy is transferred further down. There was a researcher in the early 1900s named Dr. Ekman, and Dr. Ekman realized that the wind direction of some ice, or he measured the ocean, the wind direction, and it was in one direction, but then he correctly hypothesized that the ice that he noticed was not moving directly with the wind, but in fact, slightly off to the right. He was in the Northern Hemisphere, and so as a result, he hypothesized that ocean currents at depth are going to have more of this deflection. And so the further you move down in the water column, the more this deflection is going to occur. And so if we think of these waters as individual sheets, we can map the movement of this water as a result of this Ekman transport. And so this means that when the winds are moving right along the coastline here, since we're deflecting winds to the right, that means that as that wind is moving in the upper image along the coast, deflecting to the right, what's going to happen is some of that water movement is going to get pulled down. And this is known as downwelling. In the lower image, the wind is moving in the opposite direction, again, deflecting to the right. So it's actually going to pull up some of the water from depth. We're going to learn that that cold water has a lot more of the dissolved oxygen. And so if you're bringing up new dissolved oxygen and nutrients, you're going to have abundant amount or microbes, and in this case plankton. And so this plankton is going to this upwelling is going to be really, really important for food chains, which we'll get into here in just a second. So a surface that moves water away from the shore is moving water away from the shore is going to be called upwelling, because if it moves the water away from the shore, it's going to bring up additional water to fill in that region. This is not only true near the shoreline, but this Ekman transport is actually going to cause some upwelling right along the equator, particularly in the Pacific Ocean, where we have this really large gyre. And this is really, really important because this can actually cause lots and lots of upwelling off the coast of Alaska, off the coast of South America, or a lack of upwelling. And so if we have a lack of upwelling, this is called an El Nino year. And what is happening right now is lots more upwelling is taking place, and this excess amount of upwelling is causing a La Nina year. And so in the fall of 2020, it looks like it's going to be a La Nina year for this massive amount of upwelling, which has implications, which we'll get into in a meteorology chapter. So the combination of all of these different transporting the circulation due to surface winds, as well as density-driven water, deep water movements, is going to create what's called thermohaline circulation. And this is going to be caused from density of water. Water that's going to be most dense is going to be cold, salty water. And so one of the driving forces is in fact this Gulf Stream, where this water around the equator is really, really salty. And then as the water is being pushed and deflected, it's going to cool off. And so you're going to end up with some really cold, salty water. Well, what happens when it's really heavy? It's going to mix down. It's going to follow, move in this general direction, either get pushed up into the Indian Ocean, where it hits the subcontinent of India, and in which place it's pushed up to create some upwelling, and then this water is going to be moving in this standard pattern of thermohaline circulation. The rising and sinking due to density differences in the ocean is called the thermohaline circulation. So when we start looking at winds, the periodic up and down movement of wind caused from winds to create visible troughs and crests are known as waves. And when we just like when we looked at earthquake waves or optical waves, these are all, or water waves, they all have the same mechanism, same terminology when we start looking at these. When you start looking at water, you can have smaller waves called ripples, which are developed due to the elastic behavior of water, the ocean surface, and surface tension. But when we start looking at waves, once these waves build to significant size, the gravity is causing them to rebound, so they move up and down and up and down. And so if we take a look at an object in the water, this dot being this water, this particle in the water, this yellow dot is moving up and down, up and down. It is not moving along the shore. It's only when the wave breaks that we actually have any horizontal movement of this water. And so when we start looking at these wave trains, when a wave builds up sufficient size, the gravity is causing it to rebound and moving up and down. And so when we start looking at the waves, the top of the wave is called the crest, the bottom of the wave is called the trough. The difference between The crest to the trough is called the wave height. If we divide that by 2 or measure it from the middle portion of the wave, we have the amplitude, 1/2 the wave height. And the period is the amount of time it takes for the wave to go from a crest to a trough, from a crest to a trough. So one successive crest or one successive trough. If we start looking at from successive crests or successive troughs, this is known as the wave length. And the wave movement at the surface is going to influence the water underneath. Eventually, we'll get to a point that there is no energy being transferred in the surface waters, and so this is known as wave base, and it's usually 1/2 the wavelength is the wave base. And so when we start looking at the size of these waves, there's a number of different factors which are going to influence the size of the waves. First of all is the strength of the winds, and so that's if we have 50-mile-an-hour winds, it's going to create bigger waves than if we had 5-mile-an-hour winds. The fetch is the distance over which the winds are blowing. So if you have bigger bodies of water, you're going to have longer stretches that energy can build up. And then the length of time that the wind is blowing. And so if the wind is blowing for just a short period of time, it's going to create smaller waves, longer periods of time, longer waves. So there's 3 different factors which are going to influence the size of the waves: the strength of the wind, the fetch, and the length of time that the winds are blowing. Now, as these waves are propagating through the water, every once in a while you end up with a rogue wave. A rogue wave is the sum is going to be a result of all of the energies passing through this locality. So if you have 2 waves coming together, what's going to happen is the energy is going to combine, and if we have a trough and a crest meeting, it's going to cancel each other off. But every once in a while, as these waves are propagating through, you can end up with a crest and a crest being meeting. And if you have 2 crests meeting, what can happen is it can cause a really large wave called a rogue wave. So when we start looking at these areas on the ocean, we have different parts of the water that we can look at. And so one area that is a very, very harsh environment is known as the littoral zone or the intertidal zone. This is the area between high tide and low tide. We'll talk more about tides here in a few chapters. And then we have the neritic zone. Now, on passive margins, and where we have no plate boundary, you're in the middle of a plate, you can switch from continental crust to oceanic crust. And so you actually do have a sizable continental shelf, where we can look at the east coast of the United States or the Gulf of Mexico in the United States. We have a large continental shelf. During times of glaciation, there's water in the ocean, sea level would drop, and so these continental shelves would be exposed. And so the littoral zone could be shifted further to the right on this image. If we had the ice caps melt, the littoral zone would move inland. And so when we start looking at this littoral zone, it's this area that is between high and low tide. And then the neritic zone is that area of that continental shelf. We go beyond the continental shelf, where we transition from continental rocks to oceanic rocks. We remember that oceanic crust is less thick. Continental crust is much thicker. And so isostasy tells us that not only is there things sticking up, but they're also sticking down. And so when you transition from the continental crust to the oceanic crust, there's going to be a very steep slope there, and that is known as the continental slope. And when we go beyond the continental slope, we're going to be in the oceanic zone, beyond the continental shelf. We have some organisms that are going to be on the bottom of the ocean, and so we call these benthic zone. Benthic meaning bottom. The pelagic zone is the area that is above that benthic zone. So when we start looking at ocean zones based on sunlight, we have the portion of the ocean that is receiving sunlight, the photic zone, and the boundary being the twilight zone. We have that upper surface where photosynthesis is really going down, really happening quite a bit. That's called the euphotic zone. Anytime you have an A in front of the word, it means absence or without of. And so this is when we start looking at the midnight zone, known as the aphotic zone. This is the area that does not receive sunlight. And then we down there in the abyssal depths. So when we start looking at ocean life is broken down into a couple of different categories. The first method that we can break down are modes of transportation. And the first one is the first category that we're going to look at are the wanderers or the drifters. And these are called plankton. The word plankton means wanderer or drifter. And it's the same origin that we get the word planet, which drifts across the night sky. More on that in the chapter on astronomy. And so these plankton are drifting associated with those surface and deep water currents. They're just floating around, going with the flow, literally. And there's two main categories of these plankton. The first one being phytoplankton, using light for their energy source. And then the other ones are using zooplankton. Just like humans, we can't produce our own energy. We can't convert the energy from the sun directly into sugars, and so we're going to have to rely on those phytoplankton. So if you are eating something else, you're a zooplankton. If you're a plant, you're creating your own using photosynthesis, then you'd be a phytoplankton or phyto. And then if you're an organism that can swim, you'd call nekton. If you're on the bottom of the ocean, you can see benthos organisms right on the ocean floor. And so organisms that live just on or above the ocean floor would be organisms on the bottom of the ocean. And so when we start looking at these organisms, there's a lot of them, and we're studying them for a number of different reasons. Here's some microscopic little organisms. Here, some of these phytoplankton contain chlorophyll, and they photosynthesize their energy. Then we have zooplankton, which eat other organisms, and so we can see some of these are kind of famous ones. Diatoms are very famous phytoplankton, and then zooplankton are organisms that eat other phytoplanktons or other zooplankton. Then we have those nekton, or the organisms that can swim, and they include things like marine mammals and whales, dolphins, and fish, and sharks. And then those benthic organisms, those organisms that live on or right at the sea floor, things like corals and seaweeds and sea cucumbers. Now, if we want to see how the interaction between these organisms occur, we can devise a food web that look at each individual group organism and what it's eating and what's eating it. And so we can develop these feeding relationships called food webs. And so we can start looking at why we would actually be interested in doing this is to see what the impact is if we start altering this food web. If we understand, if we lose one organism in this food web, what is the impact going to be? And so food webs usually start with primary producers called autotrophs, auto-self life. And so these are organisms that are going to extract nutrients and from non-living sources and use those to generate their energy. And then the heterotrophs, like we are, organisms which are not primary producers. And so we are going to be relying on those primary producers. And so if you are a primary producer, an autotroph, you definitely want to make sure that you have some nutrients. And so some of the nutrients that are fairly common in the ocean are things like phosphates, nitrates, and iron. And if you didn't have these things, you wouldn't be able to produce. In fact, when we start looking at there are parts of the ocean that don't have these nutrients, and if you don't have these nutrients, you're not going to be able to, you're going to limit the production of those autotrophs. The other thing that's going to be needed for respiration of the zooplankton and other marine organisms is going to be oxygen. And so oxygen is enters the ocean through the surface, can then diffuse upward or downward, or from photosynthesis. Now, the decomposition of algal blooms is going to produce zooplankton that can reproduce and eat up those microbes very, very quickly and create something called a dead zone, because they're used up all the oxygen. And so then you'd have an area that would have no oxygen. This is a real big problem in the Gulf of Mexico, because if we have additional nutrients coming in, we have very fast algal blooms and then everything eating these algae. So it creates hypoxia in these dead zones. So we can use satellites, once again, to look at different ingredients in the ocean. In this case, we're looking at chlorophyll. And I can tell you that looking at this image, the green is representing high concentrations of chlorophyll. So this tells me this is taken in the spring or summer, most likely in the summer, where we have a lot of photosynthesis at the near the northern hemisphere. And so right in this region. So understanding all the different life in the ocean, or starting to understand the life in the ocean, is a great way to stop this chapter. So we'll pick up more on the ocean in our next chapter, chapter 16.